Yeah, no worries. I'm recording. Yeah, no worries, Danny.
Okay. So I'm not sure if any of you actually came to the other session that I gave. I think that was 4 days ago, on June 26th. But yeah, so essentially, the lesson that I'm about to give now is kind of like it's the same topic, but obviously, like, since this one's an hour and last time was half an hour, there's gonna be more content. So yeah, just to let you guys know, if any of you were actually here on June 26th. Yeah. So yeah, so this is the sample lesson, obviously, as you heard Mr. Wang say. So here on the screen, I just have a little bit of like the course schedule and the topics that we're gonna cover. Again, if you're here a few days ago, this will be familiar. Otherwise, just stick with me for a second. So yeah, so this is so the course is gonna be over 4 weeks. 3 of the weeks are 3 days, and one of them is just 1 day. On the first week, we're covering so like kind of like the basics of algebra, just to make sure like everyone's on the same page. So like algebraic equations, word problems, like all that, kind of like all the stuff to get you started, essentially. And then over the second week, we're going to be going into geometry, which is another like really important thing to know in competitive math. And over the third week and the fourth week, we're going to go over like some of the kind of like the other topics, the ones that we didn't cover in the first 2 weeks. So like you can see, we have prob stats, there's rate problems, permutations and combinations, and then just like kind of like unique problems. So yeah, that's the course schedule, and now we can jump into the lesson for today here. So yeah, it's the grade 7-8 Gauss open class. And yes, I'm going to mention once again, if you're here on June 26th, there is going to be a lot of repetition, but that's it. But there will also be some new content, so stick with me. But so yeah, we're going to be going over patterns and sequences for today's lesson. So first of all, I think it's important to like say like, why does it matter that we're learning this, right? So like patterns and sequences, like sure, it might be a cool concept, but like maybe it has no applications in competitive math. Like it's in my opinion, it's always good to like know the applications of something you're learning. So first of all, like pattern recognition is an important skill to have. It's like definitely both like inside and outside of pattern problems, and even like outside of competitive math, it's really good to have like pattern recognition skills, so that you can like make observations, and that helps you solve problems. And it also comes up frequently on contests, as we'll see with all the sample problems. And patterns and sequences also leads into another concept called sequences and series. And so this is like a more advanced concept. We will go over them in one of the sample problems, but essentially, they're often like explicitly tested on contests. So like problems with sequences and series, a lot of the time they're nice to you, and they say, okay, so this problem is about sequences and series. And a lot of other problems, like sometimes they don't like give you that benefit, and you have to figure out what the problem is about yourself. So yeah, that's a reason why it's good to be familiar with patterns and sequences and series, so that way you can like solve those problems really quickly, because again, they tell you right away this is what the problem is about. So here at the bottom of the page, we have just an example of a sequences and series problem. This is from the Euclid contest, which you may know as like it's pretty much the toughest contest that the CEMC gives. And this was problem 6 from this year. You can see like it talks about arithmetic and geometric sequences. So it's definitely something that's going to be relevant, not only in the Gauss contest, but also in the future when you look to take more contests. So like I guess now I'm going to talk a bit about like what we're going to try and learn in this lesson. So first of all, I think the question, obviously the question is like, what should we know, right? At least like by the end of the lesson. So first of all, we should like be able to figure out like if patterns are involved in a problem. So like so one example of that is like a problem where you're asked to find like the 100th or the 10,000th term in a sequence, right? So that's definitely a case where you want to like use patterns and figure out, and that way like you don't have to like write out 100 terms or write out 10,000 terms. That's usually not very fun. So yeah, that's definitely one example. And obviously, yeah, we'll go over more examples of those in the sample problems. But also, So here it's probably a good time to say, so what is a pattern and what is a sequence? Because these are like some of the words that like you've heard me say a lot and I haven't really defined them. So we're gonna do that now. So one example of a pattern here, as you can see, is red, blue, green, red, so on and so forth. So a pattern is just like a bunch of things that repeat itself. You can see that here, like the pattern of the three colors like repeats itself again. An example of a sequence, it's a set of numbers, and it goes forever. So the definition for a sequence is like really broad. You can call almost any like series of like any set of numbers like a sequence. So here we have like 1, 2, 3, 4, 5. So this is your typical sequence, right? This is like how you count. It's where each term is the last term plus 1. So yeah. And we also have here an example of a sequence that's also a pattern. So we have 1, 2, 3, 1, 2, 3, 3. You'll notice that like this repeats itself, and also it's a sequence because it's just like a bunch of numbers, if that makes sense. So another thing we should or like ideally we should understand by the end of the lesson is how to figure out a pattern. So so like there's two main ways, I guess, to like figure out like what's happening in a pattern. So the first way is to find the find the first few terms and extrapolate. So essentially you look at the first few terms and then you guess the next terms. And that's definitely something that like that comes up a lot, especially when you go into like tougher problems where you don't necessarily actually know like what the exact pattern is. But what you can do is just like look at the first few terms and go like, oh, look, it repeats itself. So probably does that like forever, right? And that's even though that's not the most like that's maybe not the best way to do it. And that's maybe not like the most rigorous way to do it. So like you can't be 100% sure you're right, but you can be like 99% sure you're right. And that's usually good enough. And yeah, looking for loops, again, that's something that I just mentioned. Like definitely, if you're given the first few terms or you like write out the first few terms and you notice, hey, like there's a loop here, that means it'll probably like keep going. And finally, another thing we should know is like understand how to find the nth term in a sequence or a pattern. So this is the same thing that I mentioned like earlier on when I talked about like problems where you asked to find like the 100th or the 10,000th term up here. Yeah, and another skill that's like associated with that is how to find the period of a repeating sequence or pattern. So okay, let's talk about periods. Okay, so for example, the period of the sequence red, blue, green is 3. And that's because it takes 3 elements for the whole thing to repeat itself. You'll notice that like the sequence goes through red, blue, green, and then red, blue, green again. So there's like 3 elements before like the whole thing happens again, if that makes sense. So yeah, a period only applies if the sequence or the pattern is repeating. So for example, like if we talk if you remember, like we talked about the sequence 1, 2, 3, 4, 5. That sequence doesn't have a period because it never like comes back onto itself. But yeah, so so this is sometimes useful, especially if like for example if you're asked to like find a really big number term in a sequence in a pattern that's like repeating itself, and then that way if you know the period you can do that really quickly. So yeah, now that I've gone over like everything that we're hopefully going to be able to learn during the lesson, let's jump into a few sample problems. Yeah, I found that like sample problems are usually like a really good way to show like what's happening, and yeah, like that way you can apply your concepts and improve your understanding. So in the sequence shown, each figure after the first is formed by adding 4 squares to the previous figure. How many squares form figure 2010? So you can see they're being pretty nice here, and they've actually drawn out figure 1, 2, and 3 for us. And we'll be able to use that. We'll be able to use that pretty well moving forward. But first of all, I am going to mention, so in some questions, what you can do is just extend the sequence until you find the answer. For example, if this question asks for figure 10, you can just draw out the first 10 figures, and then you would get the answer by counting the number of squares, right? But there are 2,000 figures, so you're definitely not going to be able to draw that in like a reasonable amount of time. And remember, like the Gauss is 75 minutes long, so yeah, that's definitely not going to be a thing. But at the same time, as I said, like they're nice enough to draw out the first three figures for us. So we can use that and find a pattern. And then what that does is we can like use this pattern to extrapolate or like guess forward. And then we can figure out the number of squares that form figure 2010 without having to draw out all of the figures in between. And one other thing I want to mention is even if the diagram isn't there, it's usually best to draw out the first few figures. And that's if your pattern has like geometry in it, right? So like this is a case where it's a good idea to like draw out maybe not only the first three figures, but like the fourth and the fifth as well. And then that way you can like really be sure if you find a pattern, like, oh, this is definitely the pattern. We can see it in all of these figures. Yeah. So now jumping into the question. So since the question is asking for the number of squares, we can just so we can start by just counting how many squares there are in the first three figures, right? So figure 1 is obviously 1 square. Figure 2 is 5 squares, and figure 3 is 9 squares. And the important thing here is that basically you'll notice that the difference between figure 2 and figure 1 is 4, and the difference between figure 3 and figure 2 is also actually 4, right? And so what we can say about that is the number of squares is increasing by 4 every iteration. And by iteration, I just mean like every time you go to the next figure. And this is actually described in the problem statement. You'll see that like it actually tells you each figure after the first is formed by adding 4 squares to the previous figure. So yeah, that wasn't entirely necessary, but I'm just trying to like show you like a good way to do it. If you just see a diagram on a problem during the actual contest. So then all we need to do is just add 4 squares for every figure from 1 to 2010. So for example, okay, so this is where like intuition kind of kicks in. And intuition is a pretty big thing in patterns and sequences because it's it's fairly difficult to actually like prove a lot of your guesses. Yeah, so a lot of the time, what you'll actually end up doing is just saying, okay, so here are my here are my different like figures, right? And my intuition tells me, okay, there's a pattern happening here. And then you can just go like kind of just go with your gut. This is like a section where it's not always the best idea to like rigorously prove an answer. Now, it's not going to be the same thing when we go to like, for example, algebra, right? Where if you have an algebraic equation, it's definitely a good idea to like write everything out and make sure your answer is like 100% correct. But in patterns and sequences, it's a bit of more like a guess-y subjective math. So yeah. But yeah, so all we need to do here is just add 4 squares for every figure, as I said, because you'll notice like from figure 1 to 2 we added 4 squares, and then from figure 2 to 3 we added another 4 squares. So we can guess, or in this case we actually know because it says in the problem statement. But we know that every figure costs kind of 4 squares to add on, right? So yeah, so we need to add 4 squares 2009 times. And again, a bit of a side note here. I promise I won't have side notes on every slide. Sorry. But I just want to mention, we can also find what's called a general formula for the number of squares in a figure that we can represent with figure n. And here we have n because like we don't have a specific number. We're just saying like this is like some figure. So general formulas are not needed in Gauss, but they'll definitely be useful in the future. And I'm just going to show you here a really quick like a derivation in this precise circumstance. So since we add 4 squares n minus 1 times, and since figure 1 starts with 1 square, so you notice like in the formula how like we multiply 4 by n minus 1, right? That's like you add 4 squares n minus 1 times. Yes, multiplication, very useful. And then obviously so I guess the other key thing here is you have to make sure to add 1, because otherwise your formula doesn't work for any of the figures because it doesn't take into account like the center square. So yeah, if you're ever looking for a general formula, make sure you verify it and see if like it works on like your first 2 figures. And then if it doesn't, you'll usually like that's definitely a sign that something's wrong, and you'll usually be able to say like, oh right, I forgot to like add 1 at the beginning, or like like you know, anything like that. But yeah, if you just simplify this formula, you get 4n minus 3. And this is actually the same thing as what we just discussed about like add 4 squares every figure. But yeah, 4n minus 3 is your general formula in this case. So just to, I guess so yeah, now that we've gone over like kind of like the theory of how to do like this problem and like similar sorts of problems. So all we need to do is start with 1 square and then add 4 squares 2009 times. So the final number of squares this is 8037 squares. This is just this is just simple math. And on the Gauss also you're allowed a calculator if you're wondering. So this shouldn't take very long at all in the actual contest. And so this corresponds to answer choice A. And we can verify our answer, even though that's not completely necessary. We can verify our answer by using the general formula that we just discussed. So figure n has 4n minus 3 squares. So if we put n equals 2010 in here, then we can conclude that figure 2010 has to have 8037 squares. And that actually matches the answer that we got using like the intuitive method. So yeah, that's that should hopefully that'll convince you of it that like maybe like just using your intuition is not such a bad idea in these kinds of problems. Because yeah, like a lot of the time proving your solution might be a lot more difficult than just getting it. So now we'll move on to a problem 2. So this is a bit of a more different problem, I guess. So like yeah, there's like obviously in the Gauss contest and in every CMC contest, there's lots of different kinds of problems even within like just one topic, right? So like so yeah, here I'll talk about like the problem itself, and we can delve into the specifics. But so the problem is Chris and Pat are playing catch. So standing 1 meter apart, Pat throws the ball to Chris, and then Chris throws it back to Pat. And then 2 meters apart, they do the same. They do the same thing again. So Pat always throws first, and then Chris. And then after each pair of throws, Chris moves 1 meter further away, and they stop playing when one of them misses the ball. So so this is something that like where if your visualization skills are strong, it'll definitely help you. But yeah, so essentially like they start 1 meter apart, they throw it back and forth, and then one of them moves 1 meter away. So yeah, they essentially go like 1, 2, 3, 4, 5, and so on meters apart. So if the game ends when the 29th throw is missed, how far apart are they standing, and who misses catching the ball? And then you have the option. So yeah, essentially, so in this problem, like what you need to realize is, so 29 is not that big of a number, right? So so as I've written here, like one possible solution is just write out every throw, and then you can probably get the answer. However, this is not a time efficient. Yeah, in the Gauss, it's definitely a good idea to like be time efficient because you only have 75 minutes for 25 problems. So like writing out like throw 1, like Chris got it, or like whatever it might be, right? And writing that out 29 times is probably not the best way to do it. Instead, what we can do is find a pattern and just say, okay, it definitely goes on like this, and so on and so forth. And then we can infer the 29th throw. So yeah, also I've written here like this is an easily defeated solution. That's not really okay. So like if you're actually in the contest, right? So let's say you were writing the contest right now, and you see this problem and you have no idea how to deal with patterns. It's definitely okay to write out it's definitely like okay to write out every single throw. But what I'm saying here is like since we're not in the contest, right? We're taking a class, or well, I'm giving you a sample class. So so like in this case, like it's better to learn the concepts that'll like be able to help you. Because if the problem did ask for the 1,029th throw, you're not going to be able to write them all out, right? So yeah, so like I guess this is kind of the difference between like contest and practice. So yeah, like definitely like in practice or like while you're learning, it's good to learn like the best possible solutions. In the contest, to get your extra points, just do whatever helps you get the solution. It doesn't matter. It doesn't matter like how pretty it is, especially in a contest like this where all you have to do is pick the answer. So what's the alternative to writing out all 29 throws? Well, what we can do instead is just write out the first few terms and then find a pattern. And so this time, unlike last time, if you remember last time, they just said, oh, so we're adding 4 squares every time. So essentially it's just a multiplication, as long as you can figure out that like, you know, like how many times you're adding the number of squares. But here the pattern's not actually technically given in the problem, you have to do like some reading comprehension. And yes, you do need to make a guess. But as you'll see, like there are definitely hints in the problem that will help you like that'll like push you toward the right direction. So yeah, okay, I should have gone to this part before saying that. But yes, there are some fairly obvious hints given. So first of all, there are two throwers that alternate throws. So that gives you an idea of like the pattern should have a period of 2. If you remember, the pattern is how many times like the period of a pattern is like how many terms it has before it like repeats, right? And so if there are two throwers or alternate throws, so you have like Chris is throwing, then Pat is throwing, then Chris is throwing, then Pat is throwing. So that's a period of 2. So that's something that should tip you off. So even then, it's usually the best idea to like just write out a few throws and then see what happens. So what I've actually done here is just written out the 4 throws that they described in the problem. So like throw 1 and 2 is in the second sentence. So standing 1 meter apart, Pat throws to Chris, so Chris catches, and Chris throws it back to Pat, so Pat catches. And then throw 3 and throw 4 are the same. And so the reason why I've written Chris catches instead of Pat throws is because the question actually asks who misses catching the ball, right? So we're interested in who's catching and not who's throwing. So yeah, that's just the thing. That's just the thing to note, because if you, for example, wrote like Pat throws, it's completely possible that like maybe like later on you'll forget like it just gives you the possibility for errors, and that's definitely something that we want to avoid in like a high stress situation like a contest. So yeah. And we can immediately see here that it looks like Chris is going to catch all the odd number throws and Pat is going to catch all the even number throws, right? Because Chris is like 1, 3, and then it's his turn again, so it would be 5. And then Pat is catching like throws 2 and 4, right? And once we make this observation, we can say for sure that this goes on forever, because we can go back and say, oh, look, like the process says that they go back and forth, right? So it'll always be Chris, Pat, Chris, Pat, Chris, Pat. And since Chris is doing 1, 3, so since Chris is catching throws 1 and 3, if he's alternating with Pat, he'll always have the odd numbers. So yeah. This is definitely like a very simple example. I'm sure like lots of you have played catch before. And so definitely like it's not the most challenging thing in the world, but I do want to like go through this process in detail, because I think that like it'll definitely help you when you're like trying to observe patterns, especially in like harder problems, where it's definitely not as intuitive, or like it might be like really, really mathematical, and all you can do is guess. But you'll still be following like the same process here. Like, oh, look at what I think I found, and then try and like verify it in the problem and see if it's correct. Okay? So yeah, coming back to this problem. So since Chris is meant to catch odd number throws, that means Chris has to be the one who missed the 29 throw, because 29 is an odd number. So yeah, if we look at the answers, actually, there's 3 answers that say Pat and 2 answers that say Chris. So only A and C are possible answers. Yeah, so even if this is the only observation that you make, you've already narrowed down from 5 answers to 2. Now, I don't promise that it's going to be this easy all the time, of course, but yes, it definitely happened to be easy this time. So yeah, we just I've just kept the 4 throws here, but we're not going to go for them. I just have them there so that we can talk about them. Okay, so I just have them there so we can talk about them easily without me having to like go back and then say, hey, remember this, and then yeah. So since we know who's throwing and who's catching for the 29th throw, the next thing we have to know, so the only thing left, the only thing that separates answers A and C is how many meters they're standing apart, right? So in A, obviously, it's 15 meters, and in C, it's 14 meters. And what we can do is we can make another observation on throws 1, 2, 3, and 4. So on throw 2 and 4, on the even number throws, the distance of the throw is just the throw number divided by 2. So like 2 divided by 2 is 1, and 4 divided by 2 is 2, right? So that's how you can get a formula to find how far the throw is. And we can also, like, after making this observation, right, we can also say, oh, this makes sense because they throw back and forth before one person moves away. So the distance increases every 2 throws. So yeah, essentially like a lot. Some of the time, like when you make a guess, you should be doing like a sanity check and making sure like, okay, so this guess like kind of makes sense, and I can see it in like my list of the first few terms, and so it's probably correct, right? So yeah, the distance increases every two throws as described in the problem. So yes, and we can extend this observation because yes, okay. Before saying this, I should mention we just talked about even numbers, right? This might be a little bit difficult of an observation to make because the question is asking for the 29th row, which is an odd number. But the thing is, since so this is the most convenient observation, and you'll notice like here, for odd number throws, the distance of the throw is n+1/2 meters. And so like, even though we did make the first observation for even numbers, which might be a little bit unrealistic in actual contest circumstances, you'll notice like I've done this to like make it a bit easier for me to explain. Like in an actual contest, probably what you'll be doing is looking at the odd numbers because that's the one you're interested in, and then you'll realize, oh, so it goes up 1 every 2 throws. And maybe you'll realize like, oh, we just need to divide by 2 and round up. So for example, 3 divided by 2 is 1.5, but we round up and that's 2. Or 1 divided by 2 is 0.5 and we round up. So that's 1. So like these are all completely valid conclusions. I just have it written here like a bit formally because they're slides. And yeah, that way it's easier to understand for everybody, I hope. So yeah, the distance of the throw is n+1 in brackets all over 2 meters. And we can also say this makes sense because the distance of an odd number throw is equal to the distance of the even number throw that's 1 higher. So like, for example, throw 1 is equal to throw 2 and throw 3 is equal to throw 4, right? In terms of distance, that is. And yeah, so obviously when you add 1 to an odd number, you get an even number. And so the idea of like n+1/2 and it just being like a very small bit different from n/2 for the even number throws. Yeah, so that can be like your sanity check, right? That can be what you do to make sure, okay, my guess or my answer kind of makes sense and it works on the first few terms, so we can roll with it. So yeah, I've just written the observation here again. It's the same thing as it was on the previous slide. So what we can just do is plug in n equals 29 into the expression because again we're looking for the 29th row. So the distance of the missed throw must have been n+1/2. 29 plus 1 is 30. 30/2, 15 meters. So it's not C, which you'll notice. C, obviously, like CMC is not trying to make all this content super easy, right? So C is a very close answer. So it's definitely good to like have a rigorous formula ready, so you don't guess like, oh, 29 divided by 2, that's 14.5, but then you don't realize, wait, is it 15 or 14, right? So it's definitely a good idea to come up with a formula and make sure that your answer is correct and not falling into one of the CMC's traps. So yeah, we've already gone over both of this. So the missed throw was meant to be caught by Chris, and distance is 15 meters. 15 meters. So this is answer choice A. And yeah, you just have to find the one that matches up with the answers that you came up with. So moving on to another sample problem. This one's a problem 23. We've been going over. We went over 2 problem 19s, if I remember correctly. So problem 23. There are 25 problems in the Gauss. So the closer to the end, the harder they are generally. So 23 is a harder problem. So the sum of the first 100 positive integers is 5050, and they've been nice enough to write it out for you in sequence form. What is the sum of the first 100 positive odd integers? So right off the bat, the first 100, like the first sum number of positive odd integers, that's not really something that, like, that's not really something that's super easy to visualize. Like if they asked for the sum of the first 100 positive integers, right? That's pretty easy to visualize because we know, okay, the 100th integer is 100. That's a pretty easy conclusion to draw, right? But since they're just odd integers, that's a little bit difficult. So it's a good idea to write out like what it looks like. And here I've done exactly that. So it's 1 plus 3 plus 5 plus 7 all the way to 199. And we can say that 199 is the 100th odd number because the nth odd number is 2 and minus 1. So this is if you're not familiar with this, this is like kind of like a guess you can make, right? Because yeah, so you have like 1, 3, 5, 7, and it increases by 2 every time. And what you can actually do is something similar to problem 1. If you remember the one with the squares and the one where it went on about like adding 4 every time. Yeah, so in this case, all you do is add 2 every time. But this is also like just odd and even numbers, so it's not super difficult. So now we know, so this is the sum that we want to find, right? 1 plus 2 plus 5 plus 7 all the way to 190. That's what they asked in the question. But we don't know that number, obviously. But we do know that 1 plus 2 plus 3 plus all the way to 100 is 5,050. So how can we go from there to here, essentially? That's gonna be like, that's gonna be pretty much like the main way that we're gonna approach this problem. Because we know one of the sums, but we don't know the other sum. And what we need to do is, yeah, just like go from the known sum to the unknown sum using some sorts of arithmetic operations. So also yes, I do have a hint written here. So the increase in value of each term in the sequence goes from 1 to 2. So what I mean by that is, for example, in the first sequence, right, in the one that says 1 plus 2 all the way to 100. So from 1 to 2, there's an increase of 1. From 2 to 3, there's an increase of 1, and so on and so forth. But odd number sequence, from 1 to 3, there's an increase of 2, and from 3 to 5, there's an increase of 2, and so on. And so that's very different from what we had originally. And so this is something that we need to this is I guess a bridge that we need to cross. So how can we make that happen? And so to make the difference between two terms go from 1 to 2, what we can just do is multiply both sides of the equation by 2. And you'll notice that that's what I've done here. Essentially, so if the difference is 1, right, and we multiply both terms by 2, then the difference will also become 2. Yeah. So here you'll see like we went from 1 plus 2 all the way to 100, and now it's 2 plus 4 all the way to 200, because remember, every term is multiplied by 2. And we've also multiplied the right now 10,100. So now we need to get the value of the first 100 odd integers. So like 2 plus 4 plus all the way to 200, that's actually the sum of the first 100 even integers. Yeah, because there are 100 numbers, and we just multiplied them all by 2. And obviously even numbers are numbers that are divisible by 2, right? So yeah. So to get the value of the odd integers, we need to subtract 1 from every element. This is similar to what I said like just a moment ago about how an odd number is like 2 and minus 1. Yeah, so if you add 1 to an odd number, you get an even number. And if you subtract 1 from an odd number, you get an even number. But yeah, you can realize that, so if we start with 2 plus 4, etc., and we need to get to 1 plus 3, obviously you need to subtract 1 from every element, right? So yeah, since there are 100 elements, we need to subtract 100 times in total. So yeah, that's pretty self-explanatory. So since we need to subtract 100 times from the left side, we can make the right side equivalent by subtracting just 100, right? So like 1 times 100. And so the final answer is just going to be 10,000, because it's 10,100, which is the number that we got from by multiplying 5,050 by 2. And we subtract away the 100. So it's a nice round number. It's 10,000, and the answer is B, because that's the corresponding answer choice. I am gonna point out here, there's lots and lots of ways to do this problem. And I don't know why. Yeah, so like another good way to this shows like a different way to go from one sequence to the other one. So yeah, we have the two sequences here, right? Like 1 plus 2 all the way to 100 equals that. And then, so this is the same thing that we were trying to figure out just now. But to get from each term to the next one, instead of focusing on like, okay, let's move the entire sequence down, right? We can focus on each individual term. So the difference between the two numbers in the first term of the sequence is 1 plus 0. So 1 plus 0 is 1. So the difference is 0, right? Because yeah, it's the same term. So we don't need to make any changes. For the second term, we need to add 1. So 2 plus 1 is 3, right? So we need to go from like the number on the top to the number on the bottom. And for the third, we need to do 3 plus 2 equals 5. So you'll notice like we can spot this pattern. Again, this is like kind of a guessing pattern. We can't say like for sure. but you'll notice we're adding 0, 1, 2, etc. And then you can also notice like to get from 100 to 199, you need to add 99, right? So you just go from, so like essentially, you just like have this sequence of counting numbers. So like 0, 1, 2, so on and so forth. And that's what you need to add. Yeah, again, it is just a guess, but it will be a correct guess. And that's kind of the theme of sequences and patterns. If you make a guess and it makes sense, it will probably be correct. So also just to like make what I've done here a bit clearer, if you read the numbers downward, so you'll notice like I've written 1 plus 0 equals 1, 2 plus 1 is 3, 3 plus 1, 2 is 5. So all the numbers in the first column are 1, 2, and 3, which is the first sequence, and then the last column is 1, 3, 5, which is the second sequence. So yeah. So essentially, the answer to the problem then is just so the original sequence plus adding from 0 to 99, which is the numbers that we added to get to the new sequence, right? So the sum of numbers from 0 to 99 is the same as 1 to 100 minus 100, because 0 obviously doesn't contribute anything to the sum, but we lost our 100, right? So we just need to do 50-50 plus 50-50 minus 100, and then that's also 10,000, obviously, because we've done it just a slightly different way. It's the same problem. And I do want to mention here, so this problem actually shows an example of what's called an arithmetic series. So essentially, so this is a bit complicated. We'll unwrap the two terms separately. So arithmetic in this case means okay, I'm gonna explain. So an arithmetic sequence is a sequence of numbers where you get the next number by adding some number to the first number. So for example, if you have imagine instead of 1 plus 2 plus all the way to 100, right? We had a sequence of numbers. So 1, 2, 3, 4 all the way to 100. So you'll notice that to get each of the numbers, we add 1 to the previous number. So yeah, so that's essentially the definition of the arithmetic sequence. Now the arithmetic series, that's the sum of some number of elements in the sequence. So in like 1 plus 2 all the way to 100, you'll notice like instead of items in a list, we have a sum, and that's essentially the definition of a series. So yeah, using the idea of arithmetic series, we can also solve like the problem of the first 100 odd integers. So it's like 1 plus 3 all the way to 199. The only difference here is the difference between two terms is 2 instead of 1. And yeah, that's also something that I previously mentioned while doing the problem this way. So yeah, there is a formula to solve for any arithmetic series. I recall series is the sum of a sequence. So when I say arithmetic series, it just means like the sum of all the terms in the sequence. So there is a formula for that. I'm not going to go over it because it's definitely not needed in the Gauss, and it's pretty complicated. But yeah, so there again, there's also lots of different ways to do these kinds of problems. If any of you are familiar with the story of Gauss, the Gauss himself, I know my parents told me about this a lot. But he was the one who like found the problem, like how to add 1 plus 2 all the way to 100 really quickly, or like at least like that's how the story goes, right? So if you add the first term and the last term, you get 101. If you add the second term and the second last term, you get 101, and so on and so forth. So that's how we ended up with the formula for that. Now I don't know if he actually did that, but it's definitely a story that was told to me a lot. I don't know if it was told to you guys as well, but yeah. Yeah, now we're moving on to problem 4, which is also the last sample problem I have prepared. So, I guess I should have saved my arithmetic sequence explanation for now, because this is one of the problems that just tells you, okay, the problem is about arithmetic sequence. So, or I guess sequences. So it's definitely important that like this is something you're familiar with, and like if not like you'll see how like you'll see when we go through the actual problem. But essentially like being familiar with arithmetic sequences just means like I know like how each term is derived, and I know like how we can like add, for example. So an arithmetic sequence is a sequence in which each term after the first is obtained by adding a constant to the previous term. That's a better definition than I gave. So for example, 2, 4, 6, 8, and 1, 4, 7, 10 are arithmetic sequences. So notice like 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8. We always add 2. 1 plus 3 is 4, 4 plus 3 is 7, and 7 plus 3 is 10. We always add 3. So yeah. But the actual problem here is in the grid shown, the numbers in each row must form an arithmetic sequence, and the numbers in each column must form an arithmetic sequence. And they ask you for the value of x. So yeah, you'll know. So if you just look at the grid, you'll see only some of the numbers are filled out. And yeah, you need to solve for one of them. So okay, as you've probably seen, like immediately when looking at the problem, there's almost no information. Like there are 16 cells and you're only given 4 of them, right? So we need to like go from what we know to like stuff that we don't know, and then we can get more information, and eventually we can solve for x. Because in this like initial grid, it's very empty, right? So it's going to be very difficult to figure out what the value of x is. So to find more information, the first thing we need to do is go over like the ideas behind like arithmetic sequences and how we can find like any term in a sequence. So the two values that define an arithmetic sequence are the first term and the common difference. So the first difference, so that's the value where the common is the previous term. For example, is also second, you know, the common difference is going to be 4 minus 7 minus 4, which is in a moment when we actually start solving the problem. But here I've written out, so the general formula, again, remember, the general formula is a formula you can use to calculate any term in a sequence or a pattern. I talked about it a little bit a while ago. So again, yes, this is not necessary for Gauss, but this is going to make your life a lot easier in this problem. It's going to save you a lot of work. So the general formula for a term Tn is Tn equals T1 plus n minus 1d. I'm going to explain this formula in a second, but first I'm going to mention D is the common difference, and n is the term number. So the way we represent an arithmetic sequence is T1. So like the first term is T1, the second term is T2, the third term is T3, etc. So T just stands for term, and then the subscript says like which number it is, right? So remember, we know the first term, so we know what T1 is, and we know D, right? Because those are the two things that we absolutely have to know to figure out every term in a sequence. So Tn equals so yeah, again, like if we look at this formula, right? So Tn is just the form that you want to the term, sorry, that you want to find. So we need to know the term number, obviously, because we know which term we're trying to find. And n is going to be the term number. So for example, if n was 3, right? Let's say we want to find the third term in the sequence. So if we just substitute in n equals 3, we have T3 equals T1 plus 3 minus 1 times d. So n minus 1 is 3 minus 1, which is 2. So yeah, T3 equals T1 plus 2d in that case. And so yeah, okay. So yeah, like this is something that that like intuitively should make sense, because if you think about it, right? So in an arithmetic sequence, you add d every time. So if we go back to the example with like 2, 4, 6, 8, so T1 is 2 and d is 2 as well. So if we want to find T3, the third term, which as you can see here is 6, all we need to do is go T3 equals 2 plus 2 times 2. I'm realizing these might not have been the best numbers to pick because all of them are 2, but it's important to realize like the 2's come from different sources. So T1, the 2 in T1 is because the first term is 2. the 2 and the n minus 1 is because we were trying to find the third term, and 3 minus 1 is 2. And the 2 and the d is because the common difference is 2, right? The common difference, again, we worked that, remember, we worked that out by doing a 4 minus 2 or 6 minus 4 or 8 minus 6. So yeah. So yes, that's the general formula. And I guess also one last thing I should say, intuitively, it should make sense because you're adding the common difference n minus 1 times, right? So this is like what we did back in the first problem, where we added 4 2009 times. So if you remember, we were looking for figure 2010 actually, but we subtracted 1 because you don't add the common difference for the first one, because the first one is term 1, right? So yeah, so this is your general, essentially, yeah, this is your general formula, and it'll definitely be useful later. In my solution, in this, or I guess in the solution that I've written out on the side, we're gonna use that a lot. But yeah, if you're not interested in the general formula, what you can do is just add d every time, and yeah, that also works. But I found that this is just a bit of a cleaner way to represent it, and it also like obviously usually lessens mistakes, and that's something that I think is really useful. So yeah, so essentially we need to know the first term and the common difference, right? So this is something that I just mentioned. So but the other thing that we can use to find the arithmetic sequence is if we know the values of 2 terms and how far apart they are, we can solve for any term in the sequence. So for example, if we know, let's go back to the example, right? And this time we'll use the other sequence so that not everything is 2. But let's say we know the values of term 1, or okay, yeah, you know, for the sake of argument, let's say we don't know term 1. Let's say we know term 2 is 4 and term 3 is 7, right? So using that information, we can find that the common difference is 3 because we just subtract term 2 from term 3. So we do 7 minus 4, which is 3, and that's the common. So that's going to be like the number that you add every time, because that's the difference between the two numbers that are right next to each other, right? So we can find the common difference, and then using the common difference, we can use the formula that we just talked about to find the first term, and then we can solve for any term in the sequence. So you'll see this in action here in a moment, but you'll notice on the right I've put a table, and the table is the same as the one in the problem, except I added A, B, and C, and I'll explain this in a moment. But essentially, so remember what I said about like if you know two values and like where they are, then you can solve for any of the values. So in the table, you'll always know where the numbers are, because you'll be able to see, like, okay, for example, like it says the numbers in each row and each column must form an arithmetic sequence. So for example, if let's look at the leftmost column, right, the one with the 5 and the 23. So since there are two numbers, and we know that the numbers are the first and the fourth term, right? We can see that because they're in the first and the fourth rows. So we know two numbers and we know how far apart they are. So we can solve for any of the values along that line, which is what we've written here. So like if we know two values on the line, we can solve for all values along the line. So yes, the problem has been nice enough to give us a place to start. And so, okay, so the problem with that remains, right? Because if you look at where x is, if we try to solve for the answer in one step, as we did in all of the previous problems, it's not going to work, because there's only one value that we know along the line with x. But we can, and as I just mentioned, we can only start on the leftmost column, because you'll notice like they gave the numbers such that only the leftmost column has two numbers in the same column or row, right? Otherwise, apart from that, we don't have any place to get more information from. So we could use the technique to solve the problem called value chasing. So essentially, it's like, it's essentially what I've written here. Like you solve for one value, and it gives you enough information to solve for another value, and then that gives you enough information to solve for another value. So here, it's kind of like dominoes, really. Like you can only tip. You want to tip the last domino, but you can only tip the first domino. And if you're lucky enough to like be able to have all the dominoes in between, then you can tip it, and then like they all fall over, and then you solve the problem. So hooray. Yeah. So essentially here, the way we're gonna have to do value chasing is, first of all, we can solve for A, right? Because as we mentioned, we can find out any of the numbers along the line. We can solve for A, and then you'll notice along the second row, we'll have two numbers that we know. So we'll be able to solve for B. And then along the third column, we'll have two numbers that we know. So we can solve for C. And then finally, on the last row, we'll have two numbers that we know. So we can solve for X, right? If that was a bit confusing or like a little bit fast, don't worry. I'll explain it more in depth in just a moment when we actually solve the problem. But yeah, another important thing to note is we don't have to fill out the whole table. That's definitely a thing that will cost you time and not give you anything back, because the other numbers don't matter. Like, we don't care what's in the top right corner, for example. If that's something you want to solve for, like, great, but you're probably also wasting your time because the problem is not asking for it. And unless you need it to get X, then that's not something that's really going to be useful. So okay, so on the leftmost column, again, so as I mentioned, like, this is where we're starting. So we're going to solve for A. So yeah, we're going to have to essentially repeat this process 4 times to solve for A, then B, then C, then X. So I'm going to mention later on, this is not the only way to do it, but this is probably one of the faster ways to do it. So I'm going to go through this one like carefully to make sure like everyone understands. But I'm just gonna show you, like, it's pretty much the same thing. Once you figure out the first one, it's gonna, like, the rest of them follow pretty quickly. So on the leftmost column here, we have the first term of the sequence is 5, because that's in the first row. The fourth term is 23, right? So term 4 is equal to term 1 plus 3d using the formula that we just went through last time. So the 3 here comes from 4 minus 1, remember? So it's, I'm going to go back here. So Tn equals T1 plus n minus 1d. So if we substitute in n equals 4 here, then then n minus 1 is just going to be 3, because 4 minus 1 is 3. So yeah, so if you look at the formula right here on the screen, and then we substitute in 4, and that's what we get here. That's how we know T4 is T1 equals 3d, which is 23. And then this just boils down to solving the system of equations. I'm going to go over go through it briefly. Yeah, but yeah, if any of you aren't familiar, like, feel free to ask questions about like what I've done here. So yeah, term 4 equals 5 plus 3d, because term 1 is 5. We're just substituting in that number, and that's 23. So we subtract 5 from both sides, then we divide both sides by 3. We're just solving the algebraic equation. So d, which is, remember, the common difference or the constant that's being added, d is 6. And so if we want to solve for A, notice that A is on the second row. So it's the second term in the vertical sequence, right? So it's T2, which is T1 plus 1d, which is the same as t, because remember, it's Tn equals T1 plus n minus 1 times d. So that's just 5 plus 6, because we know T1, and we just solve for d, and that's 11. And you'll notice on the top right, I've just replaced A with 11, because we just solved for that. And yeah, so we're just going to repeat the same process for B and C and then X. So for example, here, and it's just different numbers, right? So we know term 1 and we know term 4. It's actually the same thing as what we just did. So yeah, T4 equals T1 plus 3d equals 1211. So we can substitute in T1 and then solve the equation to get d equals 400. And B is term 3, right? Because it's in the third row of that column, or sorry, third column of that row. Yeah, so it's the third term in the sequence. Remember that A was actually the second term in the sequence. So we're actually gonna have to do 2d here. And yeah, so we just substitute in the numbers, and B is 811. So replace that here in the top right. And here, and okay, so I want to emphasize this one, actually. So on the third column from the left, we're solving for C, because this one, we don't have term 1. This is actually the situation I described at the beginning, where you know 2 terms and you know how far apart they are, but you don't know term 1. You can still solve for all the terms. So term 2 is equal to term 1 plus d, and term 3 is equal to term 1 plus 2d, right? This is using the same equation that we just talked about. So term 3 minus term 2, so I've essentially like put all this algebra here, just to like show you how it comes from that. But essentially, term 3 minus term 2, you can jump all the way here to the third last equal sign. Term 3 minus term 2 is just d. because the difference between any consecutive elements is D, right? So consecutive just means elements that like come like that are right next to each other, if you're not familiar with that term. But yeah, so yeah, if you subtract two elements that are right next to each other, you'll always get the common difference. And if you think about it, like since for each element, you get it by adding D to the previous element, right? So it makes sense that when you subtract them, then you also get that same number. So yeah, so since we know these two numbers next to each other, what we can just do is find the common difference by subtracting them. So you get two. So as you can see, I've gotten 202 here, and here, what we can also do is solve for term 1, right? It wouldn't be that difficult. We would be able to do the same thing with term 2 and term 1. So since we know term 2 is 811 and we know the common difference is 202, we just do 811 minus 202, which is term 1. So it's like making the sequence, but in reverse. Remember, making the sequence is when you add a number. In reverse, it's when you subtract that same number. But to solve for C, C is term 4. So we can get it in the same way, in like the same way as like regularly making a sequence, right? Term 4 is term 3 plus the difference, because they're right next to each other, and that's how you create the next term. So yeah, C is going to be 12, 15. And finally, we solved for all of A, B, and C. And now you'll notice like this is why we did it in this order, because all we actually needed is a value on the bottom row. And now we can solve for X. So this is like a similar thing. So yeah, we T1 is 23, T3 equals T1 plus 2D is 12, 15. That should say T3. Sorry about that. On the black bullet point, or like the black square. So yeah, that should be T3 is 23 plus 2D. But yeah, that doesn't actually affect the rest of the calculations. So we found, so yeah, we just subtract 23 from both sides, divide by 2, and then we get 596. And the last thing we need to do is X equals T2. It's the second term because it's in the second column, which is the same thing as T1 plus D. And that's the same thing as, well, we know T1 and we know D. So that's 619. And the answer choice here is B, because that's the one that corresponds to it. So two things I'm going to mention that you should probably note about this. One, if you're doing this on a contest, make sure your work is organized, because all of the T's and D's are from different sequences, if that makes sense. Because we're working on like this row and then that column and that column and then that row. So all of the T1s and D's are different. So it's definitely going to be a good idea to like be careful about that, because the last thing you want to do is substitute in the D from another row, and then suddenly all your stuff is wrong because you calculated the right answer, but then you substituted in the wrong one, for example. So yeah, I've had the luxury of like being able to recheck my work because I was making the slides, right? I'm not under time pressure or anything, but that's definitely something you should be careful about, and maybe even use different variable names. Although, like I would leave that up to you, like which ones to use. But yeah, it's definitely important to not like mess up which variables are which. And another thing I've written down here at the bottom of the slide, there's also other squares to go through to do this. So you don't have to go through A, B, and C in the same order that I did, right? For example, you could also do maybe like the square below A, right? It's like the one in the first column that's missing, and then like, yeah, like there's all sorts of different ways that you can get to X. I just chose A, B, and C because I think that was the first way I saw. But definitely like in a contest, maybe like you just want to fill out the boxes. Maybe you want to like maybe you want to like go through a different way. Like that's completely fine. There's lots of different solutions to this problem. Yeah. I had four sample problems. Yes, that's what I'm saying. I had four sample problems, but this is the end of that was just the end of the last one. The last thing I want to mention is so this is just a summary. So first thing, so these are the things that like we should probably have learned throughout this lesson. So first, we need to know the keywords to find if patterns might be involved in a problem. And I have might italicized because even if these keywords are there, patterns might not necessarily be in the problem. But those should be like kind of like an alarm bell, I guess. If that, I think that's a phrase that teachers use a lot anyway. So yeah, it's something that should tip you off. Okay, like I should look into the possibility that there are patterns and sequences involved. So the keywords here, I've listed a few from the previous problems, like repeat, pattern, sequence, obviously, and each, and like every sort of any sort of list. We should also like know a bit about like how to find out a pattern involved. So like the way to do that, like I've shown you, is so find the first few terms and the period, if applicable, obviously. Typically patterns are very tricky, so all you need to do is make an observation and you'll probably be right. I've shown you that, like with the odd numbers, for example, with like the +4, and like even in the capture problem, like you just guess like, oh, the period is 2, and then you can probably, and then that's probably right. And yeah, you can also test your guess by manually finding more terms. And then another thing is understand how to find the nth term in a sequence or a pattern. So either you could find how many times like the pattern repeats. So sample problem 1, remember it was the one with all the squares, and like we added 4 a bunch of times. Yeah. So like you need to find like how many times you need to apply an operation, or you need to find maybe if there's a pattern and it repeats, we need to find where it is in the pattern. I didn't actually cover a problem about this, but those problems usually involve a division and like finding the remainder. So like finding out like where it is if there's a repeating pattern. So yeah, and arithmetic and geometric sequences are special cases. And I will say geometric sequence. So if you remember, an arithmetic sequence is a sequence where you add something and get to the next number. But a geometric sequence is where you multiply something and get to the next number. So it's a little bit different, but geometric sequences are more advanced. And finally, we should have learned like how to find the sum of a sequence of numbers. So the series. That's something I discussed. Apart from arithmetic series, there are also geometric series, but that's something that's definitely very advanced also. But yeah, the main thing that we need to focus on for Gauss is be able to find a pattern from a known series to another series. And that's the problem that I showed you with like 1 + 2 all the way to 100 versus 1 + 3 + 5 all the way to 199. So yeah, that's all I have. Thanks for listening.
Thank you, Danny. You did a great job. Thank you for giving us so amazing class. Really appreciate it. Yeah, let's share my screen with you, dear students. So let me share my screen with you. So Danny is a very excellent talent. He ranked top 0.14 of Canadian Advanced Mathematics Contest. Top 1.92% of Euclid Mathematics Contest. So Euclid Mathematics Contest is for grade 12 or levels students. And he also ranked the top 1% of Canadian computing competitions. So he's also the president of the Mathematics Club and the Physics Club of Columbia High School. And he taught many students to get a significant improvement in mathematics. And he got an offer from University of Waterloo Computer Science program and University of Toronto Computer Science program and other famous universities. So I think you can learn a lot from him. So if you are interested, please email your tuition directly to canadaolympiad@gmail.com and set your password as CMC 2021. Right now, the class is finished, so the full price would be this one. The full price would be $469. And look forward to you in the Gauss class, because grade 7 and grade 8 is very important phase for your growth. You have to learn a lot of mathematics knowledge, and your grade in grade 7 or grade 8 will determine if you can go to a good high school or pre-IB program. So this is a very important phrase to you. So I strongly suggest you I strongly suggest you to follow the Danny to learn the Gauss. Hello?
Yeah, I can hear you.
Yeah, you can hear me, right? So let's see. So today's class would be over, and if you do you have any questions for us, dear students? Do you have any questions for us? Hello? You can unmute. You can unmute your speaker and talk with us. Do you have any questions? Hello? Do you have any questions for us? So you can talk with your parents, yeah, because today's class is only 1 hour. You can talk with this class is ended. You can talk with your parents if you are interested and welcome to join our class. And the method would be send the email to Canada Olympiad gmail.com. Email your information, your name, your grade, your class, your past contest performance, and to us, and also the pays tuition. You transfer the tuition to us. Okay, if you don't have any questions, so we will finish today's class. Thank you for your attending. Thank you, Danny.
Yeah, thank you. Thank you.
Thank you.